We're here to talk about the heat of fusion and the heat of vaporization, which is going to be Unit 3, Lesson 1. This is in year 2023, 2024. So if you're in a different year, this is probably not the right QR code and it's certainly not the right dates, but just an FYI. So this is how the notebook should be arranged. That's your first title page. You have 1 or 2 pages for vocabulary, and then we'll start right off on Unit 3, Lesson 1, right up there. So now we're going to talk about the heat of fusion and vaporization. I'm going to zoom in just a little bit, and we've got solids, liquids, and gases. So we'll start by just drawing a few particles. We're going to draw 9 particles. We don't have too much space, but usually you want to make them big enough so that they are organized here as a solid. And then as a liquid, we'll still stay with 9. And they are now going to be disorganized. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. And then for a gas, now they're going to be separated. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, great. So before we had to loosen the particles right here. And so that took a certain amount of energy to get from here to here. Right now, these particles are just wiggling around. They don't have that much kinetic energy. The intermolecular force, the force that holds them together, is strong enough that it can hold them together. Now, if we give them more kinetic energy, then they start to overcome, and they overcome that sticky force, that intermolecular force, and then they start to loosen apart, and they can flow across one another, and they move around, and they can translate from one side to the other. Now, if we give it even more energy, and we give them more kinetic energy, they can separate, right? Now, what we're looking at today is this process that happens in the middle. Now, this is not kinetic energy. This is actually the actual going from the organized to the disorganized. And so we have to overcome a potential energy here. And so this potential energy is known as the heat. We're just going to call it H. Stands for something else, but we're just going to use the letter H. And this is called the H of fusion, now in both directions. Now, if I am going from a solid to a liquid, ask yourself, does that require energy or does that release energy? Okay, so to go in this direction, it's going to require energy, so we're going to have to add energy. We're going to put a positive that is in this direction. But if we are in the reverse direction, it is the same number, but it's going to be negative. Okay, it's the same number though. So if this one was positive 800 going this way, this would be negative 800. All right. So, and then this is H of the heat of vaporization. Now that's VAP. Again, it's going to be positive going in this direction, but it's going to be negative going in this direction. So you have to remove heat to take it from a gas into a liquid. All right? Yes? Okay. So that phase change requires a change of energy. The energy can be described as either the heat of fusion or the heat of vaporization, and their symbols are listed here. That's the heat of fusion or the heat of vaporization. Okay. Now, the heat of fusion is the energy required to change 1 gram of a substance from a solid to a liquid. And so the units will be joules per gram because it's for 1 gram. Now, the heat of vaporization is the energy required to change 1 gram of a substance from a liquid to a gas. So there are very similar, but it's just talking about which phase change we're looking at. And I've talked about this already, but if the heat is positive, then the change is endothermic. which means it absorbs energy in this direction. If the heat is negative, the energy change is exothermic and will release energy. Okay, so now we can quantify these and really put them all together to find its normal heat. Okay, now remember that Q stands for heat, and then the H, or delta H, is the heat of fusion or heat of vaporization, right? And then M is going to be our mass. Okay, so let's do some examples. Example one, calculate the heat of fusion in joules per gram for ice if 3,340 joules of heat are required to melt 10 grams of ice. So I'm going to zoom out and I'm going to try to do this over here. I'm going to leave that over there so we can hopefully get both of them in here. All right. So for example number one, we want to calculate the heat of fusion. So that's good. We want to know what this number is. We know that it requires 3,340 joules of heat. All right, so that means that heat is Q, 3,340 joules, and then M is our mass. So that already said it was 10 grams of ice. Great. So what heat is required to melt that? All right, so now I'm going to use my formula. We have Q equals delta H of fusion times the mass. I know that Q is right here, so I'll plug in some numbers. It is a bit confusing, but this represents one term right here. It's what, four, 5 letters, but it represents one term. Chemistry does that. That's our fun thing. And then so mass is 10 grams. Okay. Now that can simply be written as just 3,040 joules divided by 10 grams, right? And we do not need a calculator, right? Because if we're dividing by 10, we just kind of cross that out. So it's going to be 334 joules per gram. Perfect. And that is exactly what the delta H of fusion for water is, all right? Because we were looking at ice, right? So this is a set value. You can actually look it up on Google it. That number will stay the same always. And what do we call that number? We call that an intensive property. That is a number that describes that substance, only that substance, and it will never change based on the amount. So that is an intensive property, the delta H of fusion and the delta H of vaporization. So let's look at example 2. We want to calculate the amount of heat released when 30 grams of water condenses. All right, the enthalpy of vaporization, delta H vaporization of water is 2,260 joules per gram. So I know that my delta H of vaporization is 2,260 joules per gram. Again, you can just go look that one up. The NIST website, N-I-S-T, NIST.gov, they are great at listing those for every single compound you can think of. We know that the mass is 30 grams, so we want to know the heat. It says calculate the amount of heat. That's what we want to know. That's the one we're missing. So we'll go back to our formula again. Q equals delta H for vaporization times M. So Q is already isolated for us, great. So all we have to do is take 2,260 joules per gram and multiply it by 30 grams, right? And I will need a calculator. So 2260 times 30 is 67,800. Okay, and that is in joules. I hope my volume didn't cut out because it connected my AirPods with my phone. But we'll see. So that is that many joules. So, but I can also put it in kilojoules. And let me just write that, and that is that's actually going to be 67.8 kilojoules. So what did I do to that number to make it that number? I moved the decimal 3 places to the left, right? So anytime you convert joules into kilojoules, just move the decimal place 3 times to the left, and a lot of times it can be a little bit easier. Now, does this answer make sense? Is this the right answer? Well, look at this. Calculate the amount of heat released when 30 grams of water condenses. So, if we condensed, which phase were we coming from? Where did we go? You're right. We went from the gas to the liquid, correct? So going from the gas to the liquid is in which direction? Gas to the liquid. So should the answer be positive or should it be negative? Aha, right? So you had to remove heat, right, for this to happen, right? So the amount of heat released, see, it even gives you a little context clue in the problem. It was released, so this is not the right answer. This is the right answer, okay? So nothing changes about how you work the problem, but when you get to that last answer, I want you to go back, I want you to reread the question again, and ask yourself, should the answer be positive or negative? This is a very important key detail, all right? A lot of times there's only one mark. If there's a 3-mark question, one of those marks is on which sign you got it. Did you get the positive or did you get the negative? Sometimes they won't even count it correct if you said it was the incorrect sign. So you have to be careful. So how much energy is transferred when 50 grams of ethanol is evaporated? Delta H VAP equals 920 joules per gram. All right. So we know the mass this time. That's 50 grams. And we know it gives us the delta H of vaporization of this ethanol is 920 joules per gram, right? And it wants to know how much energy. Okay, well, what is energy? Energy in this case is going to be heat. You probably figured that out. That's the only variable we don't have, right? So Q equals delta H of vaporization times M. So this one's going to be exactly like the problem before. We're just going to take 920 joules per gram, and we are going to multiply by our mass. I screwed that up like a soup sandwich. 50 grams. All right. So what is this number times this number? Okay, 46000. All right, so 46000 joules. Let's go ahead and write it in kilojoules. So let's write 46 kilojoules, right? Well, there were 2 sig figs here, 1, 2, and there were 3 over here. So let's go ahead and should we count that as a third sig fig? Well, let's use the least number of sig figs. So let's use 46. If we wrote 3 sig figs, that's fine too. Okie doke. So if you wrote 46 kilojoules, that's great. If you wrote 46.0 kilojoules, that is also great. Both of those are smiley faces. All right. So let's reread the problem. How much energy is transferred when it is evaporated? So evaporated was a liquid to a gas, right? So a liquid to a gas is going to be a positive number, right? So this one's going to be a positive number. You can leave it like that, or you can go ahead and write the positive. But that is all I have for you. I do not have one on the back. So go ahead and cross out that more examples on the back. Have a wonderful day.